So my poster is on the alterations and improvements of the photoacoustic flow cytometry method. To get into why we need this and what photoacoustics is, uh, right now, if you get an infection, a doctor would just look at your symptoms and give you a broad spectrum antibiotic. And they don't test what you actually have. Because of this, broad spectrum antibiotics are overprescribed universally, and that is leading towards antibiotic resistant strains of infections to pop up in hospitals and wherever else. To counteract that, we want to use acute forms of the antibiotic that are specifically made for the infection. To do that, doctors will have to test the blood to see what kind of infection you have. Unfortunately, the leading edge right now is to use blood culturing, which takes roughly 2 to 3 days to actually get a positive result to see what kind of infection the patient has. To further improve this, my system is photoacoustic flow cytometry. So sound produced from light flowing a sample that's counted. So in layman's terms, you fire a laser into this flow chamber that's described in this schematic. Once the laser intersects with the syringe pump that has the samples, it causes a photoacoustic wave to form from the energy absorbed by the sample, and that gets translated into a electrical signal that we can properly read and diagnose from there. Now, this method is a great method, but unfortunately there's some slagging points that cause it to be very slow for manufacturing. So my goal was to streamline as fast as possible this method. The first step I did was to have a direct laser coupling. Previously, they would use an optical fiber to align the laser light into the flow chamber. That method leads to reduced amount of energy going into the flow chamber because you're using glass for the optical fiber. So instead, using a direct laser coupling, you can use as much energy as you want. What I've found at roughly 8 millijoules is the optimal energy for the flow chamber before major damage occurs. So I use a direct laser coupling with no focusing lenses or optical fibers needed. It's just a laser going into the flow chamber. The next step, I did a rapid coupling method. Previously, it would take roughly 30 minutes to an hour to get one flow chamber ready to test with. And it was a painstaking method because if there's a bubble between the sensor and the flow chamber, it would cause a false positive. Instead, I would use the curvature of the transducer or the detector to make a near perfect finish between the PDMS, which is the medium where the sound travels, and the sensor, causing no bubbles to form because it's such a tight fit. The next thing I did, I wanted to decrease the amount of time it took for PDMS to cure. Originally, it would take 2 days to cure these flow chambers. I found that to be way too long, so instead I changed all the materials, and I also changed the materials to make it so it's more heat resistant, and I made it so it's roughly 3.1 hours to actually make a flow chamber. Way drastically different from before. The last thing I did was to encapsulate this entire method within one desktop enclosure. This way it's way more safe and no one has to be worried about accidentally getting injured from the laser and overall just being more of a controlled environment. As you can see in this photo, I have all the instruments that's located in the schematic as well. So that way it's completely safe, and whenever the laser is on, you can close the entire enclosure so no laser light leaks out. And to finish off, I've completely decreased the amount of manufacturing time from 2.5 days to roughly 5 hours, completely revolutionizing the way we do these tests. And an acknowledgement to my dad, who always answered all my questions about engineering stuff, and to Mark Kaz to make me some custom metal parts. Thank you very much.